All right, if you've ever spent any time with C, you have definitely run into its most famous and, let's be honest, most infuriating error. Today, we are going to pull back the curtain on the segmentation fault. We're going to break down exactly what it is, why it keeps happening, and how you can finally get the upper hand. So let's jump right in. You know the feeling. You've been deep in the zone. You finally compile, you hit run, and then, bam, segmentation fault. That feeling is just, the worst. It feels like your program just slammed into a wall for absolutely no reason. But I promise you, there is always a reason, and just understanding it is half the battle.
So what is actually going on here? Well, in a nutshell, a segfault is your operating system playing security guard. Think about it like this. Your program gets its own little chunk of memory to live in. A segfault happens when your code tries to wander outside its designated area and poke around where it's not supposed to. The OS sees this, and to prevent any bigger problems, it just shuts the whole thing down.
Now that might sound a little abstract, but the reasons your program goes rogue usually boil down to just a handful of really common mistakes. We're about to walk through the 5 biggest culprits that cause your code to trespass into that forbidden memory. First on the list, the all-time classic, trying to dereference a null pointer. This is probably the #1 cause of seg faults, especially when you're just getting comfortable with C. So, a null pointer, by its very nature, points to absolutely nothing. No valid address, just a void. When you try to read or write data at that nothing address, the system just throws its hands up and crashes. The fix, though, is beautifully simple. A quick little if pointer not equal to null check before you use it is all it takes to avoid this headache entirely. Next up is a mistake that trips up everybody sooner or later, especially when you're working with arrays. And that's trying to access memory that's out of bounds. You see, C gives you a ton of power, which is great, but it expects you to know what you're doing. If you make an array with 10 slots, C will happily let you try to access slot number 11. The problem is that 11th spot doesn't belong to your array. By trying to access it, you're trespassing. And, you guessed it, that triggers a seg fault. So always double check your loops and your index numbers. Because number 3 is a big one, stack overflow. And no, I'm not talking about the website that saves us all on a daily basis. I mean literally running out of a type of memory called the stack. So every time you call a function, a little bit of memory gets used on the stack. Normally, that's totally fine. But the stack isn't infinite. If you have a recursive function, one that calls itself, and you forget to tell it when to stop, it'll just keep calling itself, piling more and more onto the stack until it runs out of space. And when the stack overflows, you get a segmentation fault. The fix here is making sure every recursive function has a solid base case, a clear exit strategy. All right, coming in at number 4 is a particularly sneaky one, using a variable, especially a pointer, that you never gave a starting value to. Here's the deal. When you declare a pointer but don't initialize it, it's not empty. It's actually holding whatever random garbage value was already sitting in that bit of memory. If your code then tries to use that garbage as a real address, well, who knows where it's pointing? It's a total gamble, and it often ends in a crash. This one's an easy habit to build. Just initialize your variables the moment you create them. And finally, our 5th common cause, getting your pointer math wrong. Pointer arithmetic is one of C's most powerful features, but you know what they say, with great power comes great responsibility. When you add 1 to an integer pointer, you're not just adding 1 byte. You're actually telling it to move forward by the size of a whole integer, which is usually 4 bytes. If you mess up that calculation, you can easily send your pointer way off into an invalid part of memory and crash. The key is just to be super careful and deliberate with your pointer math. Okay, so we know why seg faults happen, but what do you do when one pops up? Staring at your code and hoping for the best is not a strategy. We need tools. Let's talk about your debugging toolkit. I mean, this slide really says it all, doesn't it? On the left, we've got the path we've all been down, just guessing, getting frustrated, and wasting hours. On the right, we have precision, we have insight. The difference between these two worlds is simply using the right tools for the job. Let me introduce you to your 2 new best friends, GDB and Valgrind. GDB is like a detective for your code. It lets you run your program, and when it crashes, it freezes everything so you can inspect the crime scene, see exactly what line caused it, and what all your variables looked like. Valgrind is more like a memory watchdog. It watches your program run and barks anytime it does something sketchy with memory, often catching bugs before they even cause a crash. But you know what's even better than being a master bug hunter? writing code that doesn't have bugs in the first place. The real endgame here is to build good habits that prevent these things from ever happening. And this right here, this is your cheat sheet. It's so simple when you lay it out like this. Every single pitfall we just talked about has a direct preventative habit you can build. Instead of just hoping a pointer isn't null, you validate it. Instead of guessing with array limits, you check your bounds. If you can turn these habits into muscle memory, the number of segfaults you see will absolutely nosedive.
Ultimately, this isn't just about fixing one type of error. This is about fundamentally shifting how you think about writing C code. It's about building real, solid confidence.
It is so easy to see a segfault as a roadblock, as a failure. But what if you saw it as a learning opportunity? Every time it happens, your program is literally telling you, hey, right here, there's a weak spot in how we're thinking about memory. Fixing it doesn't just fix the bug, it makes you a smarter developer. So, if there's one thing to take away from all this, it's this. Don't just fix the crash. Take a second to understand why it crashed. Once you truly get the causes, the null pointers, the bounds checking, the stack issues, you're no longer just coding. You're engineering. You're building software that you can actually rely on. So you are now armed with the knowledge to not only fix one of C's most intimidating errors, but to actually prevent it from showing up. That frees you up to think about the cool stuff, the creative stuff. So I'll just leave you with this one question. Now that you can crush these bugs, what awesome thing are you going to build?